Today we're going to be talking about 8.3. This is a section on vectors. So really quick, vectors, they're measured by both direction and magnitude. Okay, so that's a little ambiguous. We'll be getting some concrete examples in just a second. And then scalars only measure the magnitude. Okay, so for example, if I were to tell you that I'm going 30 miles per hour, right, then that's a scalar. Okay, so it only tells you the scale of where I'm going, or how fast I'm going. Now, if I tell you I'm going 30 miles per hour north, right, because that has a direction as well as a magnitude, that's a vector. Now, if I tell you I'm pushing something with a force of 13 newtons, okay, since there's no direction, I'm not telling you where I'm pushing it, that's going to be a scalar. And finally, if I tell you I'm moving something 13 newtons up, then that's a vector, since it has both a magnitude and a direction. Now, the way that we draw vectors is that we draw them using arrows. All right, so the length of the arrow is going to tell you about the magnitude. So for example, the magnitude of this vector here, I labeled it 50. And the direction of this is up, or north. This vector here, see this arrow is about half the size of this one. So it has magnitude 25. All right, and it is going to the right, or east. All right, so these two vectors are not the same since they don't have the same magnitude or direction. Now note that this little school of vectors, they're all the same. So we say that these vectors are equivalent or equal since they all have the same length and they're all going in the same direction, right? They're all kind of heading northeast. All right, so when we have a vector, we kind of denote it special. So for example, a vector a vector A is written as A, and you'll see this in bold type in the book. It's not very easy for me to write in bold, so just assume it's bold. So vector A is written as we have this pointy bracket, A1, comma, A2, and pointy bracket. So what are A2 and A1? Well, A1, we can kind of think of that as our x coordinate if this was the point. Okay, but what that tells us is its horizontal component. All right, so that's telling you how many steps I need to move to the right or to the left to get to the tip. And then this vertical component, A2, tells me how high I need to go to get the tip. All right, so it's how many over I need to go from the tail and how many up I need to go to get to the head. And then we have the length of the vector is denoted by this double bar here. Right, so we call this double bar, those aren't absolute values, that's the magnitude or the length of our vector A. Now, if you notice that if we know this angle here, then cosine of that angle is equal to our horizontal component, which is A1, right, divided by the length of the vector, right, which would be our hypotenuse if we had a right angle here. Same thing with sine of theta, that's going to be the side opposite over hypotenuse, so that's A2 over the length of A. Okay, so that should look kind of familiar, as should this, because remember when we were, if we had a point x, y before, and we had the length of our ray, which would be r, then remember that r was equal to the square root of x squared plus y squared. And similarly, that would be similar to x over r, and that would be similar to y over r. Okay, so we definitely have some similarities going between vectors and chapter 6. Okay, so as you've seen, we usually have vectors starting at the origin. but sometimes we can have vectors starting kind of anywhere and ending anywhere. So let's say that I have a vector, and let's say it starts at point P, and let's have point P be P1 and P2. So my P1 is going to be my x value, and P2 is going to be my y value. And let's say that it ends at Q, which would be my point Q, which has Q1 and Q2. So Q1 would be my x coordinate in that case, and this would be my y coordinate. All right, then we can denote that vector as PQ, and we draw this little weird arrow thing up here, equals, so we take the x component from the last one and subtract the x component from the first one, comma Q2 minus P2. All right, so let's do an example. Let's say that I'm starting at 4, 3, and I'm ending at 7, 8. All right, so 4, 3 would be about right here. That's my P point. My Q is 7, 8. So it's going to be about right here and here. So that's my Q. Now the direction of my vector is important. Okay? So if I'm starting at P and I'm going towards Q, then my arrow goes at the end at Q. So I've just drawn the vector PQ like this. Okay. Now if it had been QP, that tells you that I start at P and then end at, or I'm sorry, start at Q and then end at P, so my arrow would be facing in the opposite direction. Okay, so now if I wanted to calculate this out, I just drew it graphically. So if I wanted to calculate it out, then I'd have PQ equals Q1 minus P1, comma Q2 minus P2, and then I would get that that vector is 3, comma 5. So what that tells me is that I need to go 3 over, 1, 2, 3, and then I need to go 5 up, so 1, 2, 3, 4, 5, to get from the tail of my arrow to the head. Right, so even though this isn't positioned at 0, 0, it's still going to have a horizontal component of 3, that's my horizontal, and a vertical component of 5. So it's going to tell me how far over I need to go and how far up. Now if this had been negative 3, that just tells me that I need to go the left 3, and let's say it had been negative 5, that means I need to go down 5, and this would have been facing in the opposite direction. Okay, so let's try another one. So let's find PQ if P is negative 3, 2, and Q is 4, negative 7. All right, so let's do this numerically first. So we're going to have Q1 minus P1, which is negative 3, comma negative 7 minus 2. All right, we do the algebra on that, and we get that our horizontal component is 7, and our new vertical component is negative 9. All right, so I already plotted out the points PQ. So if I go ahead and I draw a line down, now remember, I'm going from P to Q, so the head of my arrow is going to be down here. All right, looks pretty good. Now what this is telling me is that to get from the tail to the head, I need to go over 7. So 1, 2, 3, 4, 5, 6, 7. Then I need to go down 9, right? So that negative means I'm going down. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. Perfect. All right, so I need to go 7 to the right and 9 down. All right, let's talk about how we can operate these vectors together. All right, so let's say I have two different vectors. So let's say that I have a vector A, and it's denoted by A1, A2, and I have vector B, which is B1, B2. Then adding two vectors together is the same as adding their horizontal components together and their vertical components together. right, A minus B is pretty intuitive. It's going to be subtracting the horizontal components and subtracting the vertical components. And then if we let k be a real number, so it could be negative, positive, a decimal, doesn't matter, then k times a vector v is equal to k times the components, which means that we just multiply the interior components by k. All right, so we're going to do some examples and look at drawing them out. So if we let a equal a1, a2, and we let our vector b equal b1, b2, and I just kind of drew a rough sketch of what a could be and what b could be, right? So notice that these are two different vectors, right? This one's going in this direction and has a different length, and b is going in this direction and has a different length than a. All right, so then we can think of adding these two vectors together by connecting them. So notice I connected a tail to head, and I connected b from the tail to head, and then this line down here I connected from the tail of a to the head of b. Okay? And now what that vector is down here is that we call this the vector a plus b. So I created a whole new vector. All right, so let's see what that looks like in an example. So remember, when we're adding these together numerically, it's as simple as just adding a1 and b1, a2 and b2. But then when we look at it graphically or in a picture, we're connecting tail to head, and then finally tail to head again. And then this new blue vector here is going to be a to b, or a plus b. Right, so let's add together a plus b, and we're given that a equals 3, 4, and b equals 3, 0. Right, so if I do that, oops, add ink on this one. So if I do that, then I have a plus b equals, it's going to equal a1 plus my b1. It's going to be 3 plus 3, comma, a2 plus b2. That's going to be 4 plus 0. That's going to give me 6, comma 4. All right, now let's do this graphically. So I'm just going to draw a from the origin and b from the origin. All right, so when I draw a from the origin, that means that its tail is going to start at 0, 0, and then I'm going to go 3 horizontally and 4 vertically, so it's going to be about right here. All right, so this is my A. And then my B, I go over 3, and it's 0, so I don't go up at all. So it just goes like this. Now what I can do is that I can kind of phantomly pick up this vector and just place it at the head of A. All right, so if I pick it up and move it a little bit, notice that these two vectors, even though they're at different spots in the graph, they're going the same direction, so they're both moving directly to the right, and they have the same length. So the same vectors, I just spatially moved it. So this is also B. Okay. I also could have added the tail of A to the head of B. All right, so had I done that, it would have looked like this. And that's A. So because addition is commutative, you could have done either of these. And watch what happens. So if we connect the tail of A to the head of B, we get this line. And had we done in reversed order, so had we done B plus A, we would have connected the head of, or the tail of B to the head of A and ended up in the same point. So this new vector here is A plus B. So the tip of this guy here should have a horizontal component of 6 and a vertical component of 4. So let's check that. So we start here and we go 1, 2, 3, 4, 5, 6. That's good. Then we go up 4, 1, 2, 3, and 4. Perfect. So that's how you can confirm adding vectors graphically. Okay, and don't forget that you can add them either A to B or B to A. We end up with the same answer. And see, this is a neat little parallelogram we've made. We're going to get to parallelograms a little bit later. Now, unfortunately, vector subtraction isn't as neat. There's just one little trick. So this should be a minus. Okay? So if we take A minus B, that's the same as A plus a negative vector B. All right, so if we let A equal 5, 7, and we let B equal 2, 3, then if we take A minus B, that's the same as A plus a negative B. All right, so really quick, let me just make a note that negative B is just going to be the negative of the inside. So that's going to be negative 2 and negative 3. All right, so if I add these together, what I'm going to have is I'm going to have 5 plus, now this is a negative B, so I'm going to look over here. It's going to be plus negative 2, comma 7 plus, now this is negative B still, so we're going to do plus negative 3, and that's going to give us the vector 3, 4. Okay, so now we're going to draw it graphically. We're going to change it up a little bit. So my A vector is 5, 7, so we have 1, 2, 3, 4, 5, and 7 looks like it's about right here. Okay, so that's my A. My V vector is 2, 3, so we have 2 here, and then 3. All right, so that little guy is my B. That might be a little hard to see. Sorry, guys. Okay. But now, I'm not adding A to B. I'm adding A to negative B, or subtracting A from B. So in green, let me go ahead and draw what negative B would look like. So negative B is going to go negative 2. So negative means I'm going to the left. And then negative 3 means I'm going down. So this green one is negative B. Okay. Notice that they're mirror images of each other. Okay, so it looks like I just took B and went the opposite direction, the same distance. Right, that's important. So now what I'm going to do is I'm going to add negative B to A. So even though this is a negative vector, I'm going to add it the same way I did the other one, so it's going to be tail to head. So I'm going to go here and add negative B. Okay. I also could have added negative B to A, which would have been if I started at the head and just took this vector and dropped it down. So it would look like this. Okay. Now, my last vector, or my, what do you call it? Oh, my final vector, A minus B, or A plus negative B, is going to go from here, from the tail of A, to the head of negative B. Right, so now this vector is A minus B. All right, the picture is a little cattywampus, so let me draw it a little bit better over here on the side. So what that is, that looks like this. So this is A. This guy is negative B. This here is also negative B. This is A again. So remember, I can either take A and add it to negative B, or I can take negative B and add it to A. They're the same thing. All right, and that vector is going to look just like this. All right, then notice if I had gone from the tail of B and gone to the head of A, it's the exact same vector. Right, so they do not change. So numerically is a little bit easier But we're going to move on a little bit later and show why this is such a valuable tool to be able to draw these and what they look like. Now vector scalar is best in an example. So let's say that we have k equals 5. So that's going to be our scalar. And we have a equals -2 or -1 and 2. Then what we're going to have is that we're going to have the ka equals 5 times the horizontal and vertical components. So 5 times -1 gives you -5. 5 times 2 gives you 10. All right, so let's go ahead and draw our original vector. So I go over 1, up 2. So that guy is my A. Okay, now let me draw my KA, which would be -5. So 1, 2, 3, 4, 5, and then I gotta go up 10. So 1, 2, 3, 4, 5. I'll just kind of eyeball this. Let's say it's better here. So now this guy is right there. So this vector is KA. And you can't see it in the picture very well, but this guy doesn't start at the tip of A. He starts all the way down here and extends upwards. All right, so we can kind of think of this as I'm going in the same direction, I'm just increasing the magnitude. All right, so a good example would be if I'm driving in a car and I'm heading, let's say I'm heading south, and I'm heading south at 5 miles per hour. I'm going super slow. Okay, we're in a neighborhood, there are kids playing ball, I'm going super slow. But then I leave the neighborhood and I increase my speed by 5. Okay, so let this vector be C. So then 5C, I'm still going south, but now I'm going quite a bit faster. Now I'm going 25 miles per hour. Okay, so that's a way that we would use magnitude, or K is that we would be able to change our magnitude. All right, so now let's go on to another example. So what if K is negative? So let's look at K equals -3, and A equals -2 and 3. All right, so that would be -3A, which would equal 3 times -2, 3. And that would give us -6 and 9. All right, so let's draw our original vector here. So we have A is -2, 3. So this is A. Okay, and then -3A goes -3. Oh, whoops, I goofed. That's a -3, which means that that's a +6 and that's a -9. Sorry, guys. So new one should be +6 and -9. So we're going to go over in the positive direction 6. So 1, 2, 3, 4, 5, 6. Then we're going to go down 9, which would be about right here. Alright, so that's going to be my -3A. So notice that that negative changed the direction of my vector, right? So not only did it increase the magnitude of my vector, but that negative sign flipped it over. Alright, so let's just use the car example again. So let's say that I'm backing up into a spot, right? I'm at the store and I'm backing up, and I'm backing up at a speed of 3 miles per hour, right? And then if I change my direction and I start going 9 miles per hour, then I'm going forward 9 miles per hour. Okay, so that changes my direction. So a negative value changes your direction. All right, parallelograms, yes. All right, first let's review parallelograms. So parallelograms, my two sides opposite each other have the same length. So these A's are the same. These two sides B have the same length. My interior angles, the angles opposite each other have the same measurement, and same for here. Now note, this is going to be very important, that if I take this angle plus this angle, that's going to give me 180 degrees. All right, so like most things in this class, this is best done through an example. So let's say I was asked to find the combined magnitude of the two forces below. Right, so I know that if I'm adding A to B, or here I displayed the magnitude, that's magnitude A equals 15, magnitude B equals 7. I know if I add them together, I'm going to add the tail of A to the head of B. That's going to look like that. And this is still A, so the magnitude of this guy is still 15. All right. And likewise, if I added B to A, then I would take the tail of B to the head of A, like so. So the length of this guy is also B. All right, now what I don't know is the interior angles. Well, real quick, what we're trying to find is this length. Because remember, we're going from the tail of A to the head of B, or from the tail of B to the head of A. Either way, we're doing the same thing. Okay, now like I was saying, what we don't know is that we don't know the interior angle right here. So we know that this is 32, but now that I've drawn that line through there, it's not going to bifurcate it perfectly. So what I mean by that is that I'm not going to have 16 on both sides. As you can see, the angle on this side is quite a bit bigger than the angle on this side. So don't just assume that it cuts it in half. But remember up here that I said that this angle plus this angle equals 180. So let's go ahead and call this angle theta 2. Right, so then theta 2 plus 32 degrees is going to give me 180 degrees. Subtract both sides by 32. I get that theta 2 equals 148. Okay, now why do I care? Well, I care because this diagram is floating out in space. So number one, I don't have an A1, A2. Okay, so I don't know what A1 or A2 is. I also don't know what B1 and B2 are. Okay, but that's okay because I don't need them to find the length of this vector here. So I'm going to go ahead and call this vector C. Now notice if I picked this triangle up and I threw it down here, so I need to find C. I know that the length of this angle is 148 degrees. I know that this side here is 7. I know that this side here is 15 long. So then how would I find out how long C is, or the magnitude of C? Well, since this is A and this is B, we'll call this guy gamma for right now. Law of cosines, yeah! So we're going to use law of cosines. So I'm going to have C squared equals 7 squared plus 15 squared minus 2 times 7 times 15 cosine of gamma. Oh, well, we know gamma. Sorry. All right. So if we go ahead and solve for C, you can go ahead and pause the video and work that out for yourself if you like to. So we're going to get that C equals 21.26. All right, now how did I know to use the law of cosines? Well, if I'm given an angle, right, and it wants me to find the combined magnitude of the two forces, then most of the time, rather than not, we're going to be using the parallelogram rule. All right, so now we're going to go ahead and move on to video 2 to finish up vectors.